Welcome! Today we are diving into LeetCode problem number 78, subsets. This problem challenges us to generate all possible subsets of a given array, which is also known as the power set. Stay tuned as we explore efficient algorithms to solve this problem step by step. The problem we're solving involves generating all possible subsets, also known as the power set, from an input array of unique integers called nums. The key requirement is that the solution must not include duplicate subsets, and the order in which the subsets are returned does not matter. For example, if the input array has 3 elements, the output should contain all subsets of those elements, ranging from the empty subset to the full set itself. The input constraints specify that the length of nums will be between 1 and 10, and each element in the array will be a unique integer between -10 and 10. The output, as required, is a list of lists, where each inner list is a subset of the input array. Looking at the first example, when the input array is 1, 2, 3, the power set includes all possible combinations of these 3 numbers. This starts with the empty subset, followed by subsets containing one element like 1, 2, and 3. Then, we have subsets with 2 elements such as 1, 2, 1, 3, and 2, 3. Finally, there's the subset containing all 3 elements, which is 1, 2, 3. Altogether, the output is a comprehensive list of all these subsets. This demonstrates how we systematically generate every possible combination of the input elements. In the second example, the input is a single element array, 0. Here, the power set consists of just 2 subsets, the empty subset, and the subset containing the single element, 0. With only one element in the input, the combinations are minimal, but the approach remains consistent. Each subset represents a different way to include or exclude elements from the input array. Now, in the third example, the input array has 2 elements, 4, 5. The resulting power set includes all possible subsets of these 2 numbers. This starts with the empty subset, followed by subsets containing one element like 4 and 5. Finally, there's the subset containing both elements, 4, 5. This example highlights how the number of subsets grows as the input size increases, following the principle of generating all combinations of the input elements. To wrap up, let's consider some additional edge cases. For a single element array like 5, the subsets are simply 5. With 2 elements, such as 1, 2, the subsets expand to 1, 2, 1, 2. When the input includes both negative and positive numbers, like -1, 0, 1, the power set includes subsets such as -1, 0, 1, -1, 0, -1, 1, 0, 1, -1, 0, 1. Lastly, for the largest input size of 10 elements, the number of subsets reaches 2^10, or 10^24. This exponential growth underscores the need for an efficient solution to handle larger inputs effectively. To solve LeetCode problem number 78, which requires generating all possible subsets of a given array, we can consider a few different approaches. The first is the brute force approach. Here, the idea is to generate all possible combinations of elements in the input array, nums. Since each element can either be included in a subset or excluded, the total number of subsets for an array of size n is 2^n. To implement this, we iterate through all integers from 0 to 2^n1, treating each integer as a binary mask. Each bit in the mask represents whether the corresponding element in the array is included in the subset. While this approach is simple and systematic, its efficiency is a concern. The time complexity is n*2 to the power of n, because we generate 2^n subsets and, for each subset, may process up to n elements. Additionally, the space complexity is also n*2 to the power of n, to store all the subsets. The main limitation of this method is that it becomes cumbersome and less flexible as the problem's complexity or constraints increase, making it less practical for larger or more nuanced problems. Another approach is backtracking, a recursive technique that systematically explores all possible combinations. The core intuition here is to decide, at each step, whether to include or exclude the current element in the subset. This structured method makes it easier to adapt to variations of the problem, such as generating subsets with specific constraints. In terms of implementation, backtracking involves a recursive function that builds subsets by making inclusion or exclusion decisions for each element, and once all elements are processed, the subset is added to the result. the time complexity remains O, n asterisk 2 to the power of n, because we still generate 2 caret n subsets, with each subset taking up to O, n, time to copy. The space complexity is O, n, for the recursion stack, plus O, n asterisk 2 to the power of n, to store the subsets. The benefits of this approach include its intuitive structure and the ease of modifying it for related problems. However, one drawback is that recursive calls could lead to a stack overflow for very large inputs. That said, this is rarely an issue under typical problem constraints. The iterative approach provides another way to solve the problem. It builds the power set step by step without using recursion. The intuition here is straightforward: start with the empty subset, represented as, and then expand it by adding each element from the array to all existing subsets. For example, if the current result contains subsets 1 and the next element is 2, we generate new subsets by appending 2 to each subset, resulting in 1, 2, 1, 2. This process continues for every element in nums. The time complexity, similar to the other methods, is O, n asterisk 2 to the power of n, as we double the number of subsets for each of the n elements. The space complexity is also O, n asterisk 2 to the power of n, to store the subsets. This approach avoids recursion, making it easier to implement iteratively. However, compared to backtracking, it's less intuitive and harder to adapt for problems requiring additional constraints or customizations. For this problem, the backtracking approach stands out as the most suitable strategy. Backtracking offers a clear and systematic way to explore all subset combinations while being highly adaptable to variations of the problem. For instance, if constraints like generating subsets of specific sizes or meeting certain conditions are added, the recursive structure of backtracking makes those modifications easier to integrate. Additionally, the implementation mirrors the natural decision-making process of including or excluding elements, which enhances code clarity. While the iterative approach avoids recursion, it lacks this flexibility and is less intuitive for extending to related problems. As for the brute force method, it's straightforward but inefficient and difficult to scale or adapt. Considering the constraints of this problem, where the input size is small, with at most 10 elements, the recursion depth remains manageable, and the performance is acceptable. This balance of clarity, flexibility, and efficiency makes backtracking the ideal choice for generating subsets in this scenario. The problem at hand is to generate all possible subsets, also known as the power set, from a given array of integers. For instance, if the input array is 1, 2, 3, the output should include all combinations of elements, such as the empty subset, single-element subsets like 1, 2, 3, and multi-element subsets like 1, 2, 1, 3, 2, 3, and 1, 2, 3. To achieve this, we must explore all possible combinations of elements without introducing duplicates. To start, we define the problem scope. For an array of size n, there are 2 caret n subsets because each element has exactly 2 choices either to be included in a subset or excluded. This makes backtracking an ideal approach, as it systematically explores all possible combinations by making decisions and revisiting them when necessary. The core idea is to design a recursive function that iterates over the array, making inclusion and exclusion decisions at every step. At each step of the backtracking process, we either include the current element in the subset or skip it entirely. Once a subset is formed, it gets added to the result list. The recursion continues to explore further combinations until the base case is reached, which occurs when the function has processed all elements in the array. At this point, the current subset is considered complete and is appended to the result list. For the recursive case, the function makes 2 calls for each element, one that includes the element in the current subset and another that excludes it, ensuring all possible combinations are explored. Implementing this approach in Python, we use a recursive helper function called backtrack. This function starts by adding the current subset to the result list, then iterates through the array from the given index, making decisions to include or exclude elements. In the implementation, when an element is included in the current subset, we append it to the current list and make a recursive call to explore further subsets starting from the next index. After recursion, the algorithm backtracks by removing the last added element to undo the decision and explore the alternative path. The recursion begins with an empty subset by calling backtrack 0. This ensures that all subsets, starting from the empty set to the full set, are generated. The recursive structure forms a decision tree, where each node represents a choice to include or exclude an element. The depth of this tree corresponds to the number of elements in the input array, and the total number of leaf nodes in the tree is 2n, representing all possible subsets. The backtracking mechanism ensures that each path in the tree is fully explored before returning to explore another branch. Backtracking plays a critical role in ensuring that the algorithm systematically explores all possible combinations. By undoing decisions after recursion, the algorithm efficiently traverses the decision tree without redundancy. This approach guarantees that no duplicate subsets are generated because the recursion progresses linearly through the input array, preserving the order of elements. The algorithm uses two key data structures: the result list, which stores all completed subsets, and the current list, which temporarily holds elements while building individual subsets. The current list is modified in place during recursion to maintain efficiency. From a complexity perspective, the time required to generate all subsets is proportional to the total number of subsets, which is 2n, multiplied by the time it takes to construct each subset, which is O(n), due to copying. Hence, the total time complexity is O(n*2 to the power of n. The algorithm's space complexity involves two components: the recursion stack and the storage of subsets in the result list. The recursion stack can go as deep as the number of elements in the array, n, while the result list stores all 2n subsets, each of which can take up to O(n) space. Therefore, the total space complexity is O(n*2 to the power of n. It is also important to consider edge cases. For an empty input array, the power set contains just the empty subset, so the output is. For a single element array like 1, the power set includes the empty subset and the single element subset, resulting in 1. Additionally, the problem guarantees that the input array contains no duplicate elements, so we do not need to implement any special handling for duplicates. This makes the algorithm straightforward and efficient in these scenarios. To solidify our understanding, let's walk through an example where the input array is 1, 2. Initially, the current subset is empty, and the result list is also empty. At the first level, we make two decisions: include 1 in the subset or exclude it. If we include 1, the current subset becomes 1, and we recurse to explore further. If we exclude 1, the current remains empty, and we recurse from there. At the second level, we decide whether to include or exclude 2. From 1, including 2 results in the subset 1, 2, which is added to the result list, and we backtrack to 1. Similarly, from the empty subset, including 2 results in 2, which is added to the result list, and we backtrack to the empty subset. This process generates all subsets 1, 2, 1, 2, completing the power set for this input. This Python implementation solves LeetCode problem number 78, subsets using the backtracking technique. The goal is to generate all possible subsets of the input array nums, including the empty subset. First, we define a subsets method within the solution class. Inside the method, we initialize an empty list result to store all generated subsets. The backtrack function is defined as a helper function to facilitate recursive exploration of subsets. The backtrack function takes 2 arguments: start, the starting index for iteration, and current_subset, the current subset being constructed. At each step, a copy of current_subset is appended to result to ensure that modifications to current_subset during recursion do not affect previously stored subsets. The for loop iterates over the elements of nums starting from the start index. For each element nums, I, it is added to current_subset, and the backtrack function is recursively called with I+1 as the new starting index. This ensures that subsequent subsets include the chosen element. After the recursive call, the last added element is removed from current_subset using pop, to backtrack and explore other combinations without the current element. The backtrack function is initially called with start equals 0 and an empty current_subset. This triggers the recursive process, generating all subsets step by step and appending them to result. Finally, the result list containing all subsets is returned as the output. This approach ensures that all possible subsets are generated without duplicates. The time complexity of the solution is O(2 to the power of n*n, where n is the length of nums, as there are 2 to the power of n subsets and constructing each subset takes O(n) time. The space complexity is O(n) due to the recursion stack and the space used by current_subset during the backtracking process. This is the Java implementation of LeetCode problem number 78, subsets. The logic mirrors the Python implementation, using recursion and backtracking to generate all subsets of the input array. Key differences include Java's type declarations, the use of ArrayList for dynamic lists, and newArrayList, current subset, to create copies of the subset. The method utilizes a helper function to handle recursive backtracking and ensures that all possible subsets are generated efficiently. To solve the problem of generating all subsets, we start with the input array nums equals 1, 2, and an initially empty result list to store the subsets. The solution uses a backtracking approach, and we begin by calling the backtrack function with start equals 0 and current_subset equals, which represents the empty subset. In the first call, we append a copy of the current subset, which is, to the result, so result becomes. Then, we iterate over the elements of nums starting from index 0. The first element, nums, 0, equals 1, is added to current_subset, making it 1. We then make a recursive call to backtrack with start equals 1 and the updated current_subset equals 1. In the second call, we again append a copy of the current subset, 1, to result, resulting in result equals 1. Continuing the iteration from index 1, we include nums, 1, equals 2 in current_subset, which now becomes 1, 2. Another recursive call is made with start equals 2 and current_subset equals 1, 2, for further exploration. In the third call to backtrack, the current subset, 1, 2, is appended to result, making result equals 1, 1, 2. Since the start index is now 2, which is equal to the length of nums, there are no further elements to iterate over. At this point, we backtrack by removing the last element from current_subset, reverting it to 1. We return to the previous call and continue backtracking further, removing 1 from current_subset, so it becomes an empty list, again. From there, the iteration in the first call proceeds to the next element, nums, 1, equals 2. This value is added to current_subset, resulting in 2, and we make another recursive call to backtrack with start equals 2 and current_subset equals 2. In this fourth call, we append 2 to result, giving result equals 1, 1, 2, 2. With no further elements to iterate over, we backtrack once more by removing 2 from current_subset, leaving it empty. At this point, all recursive calls are complete, and the final output for this input is result equals 1, 1, 2, 2. Now let's consider a larger input, nums equals 1, 2, 3. We begin with an empty result and call backtrack, 0, to generate the subsets. In the first call, the empty subset is added to result, so result equals. Iteration starts at index 0, where nums, 0, equals 1 is added to current_subset, resulting in 1. A recursive call is made with start equals 1 and current_subset equals 1. In the second call, 1 is appended to result, giving result equals 1. Iterating from index 1, nums, 1 equals 2 is added to current_subset, which becomes 1, 2. Another recursive call is made with start equals 2 and current_subset equals 1, 2. In this third call, 1, 2 is added to result, so result equals 1, 1, 2. Continuing to iterate, nums, 2 equals 3 is included in current_subset, updating it to 1, 2, 3, and another recursive call is made with start equals 3 and current_subset equals 1, 2, 3. In the fourth call, the subset 1, 2, 3 is added to result, making result equals 1, 1, 2, 1, 2, 3. Since there are no more elements to iterate over, we backtrack by removing the last element, 3, from current_subset, reverting it to 1, 2. We return to the previous recursive levels, exploring other subsets such as 1, 3, by including 3 directly after removing 2. We also generate subsets starting with 2, such as 2, 3, and finally subsets starting with 3 on its own. Each subset is appended as we progress, ensuring no duplicates and preserving the order of exploration. By the time all elements have been considered, the result contains all possible subsets for the input 1, 2, 3. The final output is result equals 1, 1, 2, 1, 2, 3, 1, 3, 2, 2, 3, 3. For the final example, we consider an empty input, nums equals. Here, the result list starts as empty, and we invoke backtrack 0. In the first call, the empty subset is appended to result, making result equals. Since there are no elements in nums, there is nothing to iterate over, and the function simply returns. The final output in this case is result equals, which is the only subset possible for an empty input. This highlights the systematic nature of the algorithm, which uses recursion and backtracking to include or exclude elements at each step. Importantly, subsets are appended as copies to prevent unintended side effects during backtracking. The overall time complexity of the algorithm is O, 2 to the power of n, where n is the length of the input array, as there are 2 to the power of n subsets in total. This approach ensures that all subsets are explored efficiently and correctly. To analyze the time complexity of this problem, we start by considering the number of subsets generated. For an array of size n, there are 2 n subsets, because each element can either be included in a subset or excluded, leading to all possible combinations. Next, for each subset that is generated, the algorithm performs an operation to append it to the result list. Copying a subset has a cost proportional to its size, which we refer to as O, k, for a subset of size k. When we add up the sizes of all subsets, we get a total sum of n*2 n1. This result comes from the fact that each element in the array appears in exactly half of the subsets. Finally, the recursive calls made by the backtracking function also contribute to the time complexity. The function is called recursively for each subset, leading to a total of 2 n recursive calls. These three factors combine to form the basis of the time complexity analysis. When we combine these elements, the overall time complexity comes out to be O, n*2 to the power of n. The n factor arises from the cost of copying subsets, while the 2 n accounts for the total number of subsets generated. Now, let's analyze the space complexity. The space usage consists of 2 main components. First, the recursive call stack. Since the recursion explores one branch for each element in the array, the maximum depth of the stack is n, making this component O, n. Second, the space required for result storage. The result list stores all 2 n subsets, where the average size of a subset is approximately n/2. When you multiply the number of subsets by their average size, the space required for result storage is O, n*2 to the power of n. Combining these two components, the overall space complexity is also O, n*2 to the power of n. It's important to note that the result storage dominates the stack space usage in this case. Now, let's compare this approach to a naive method. A naive way to generate subsets would involve iterating through all binary masks of length n, from 0 to 2 n1, and constructing subsets based on the bit set in each mask. This method also has a time complexity of O, n*2 to the power of n, since constructing each subset requires O, n, time. However, the backtracking approach is often more memory efficient in practice because it constructs subsets iteratively without pre-computing binary masks. The backtracking solution is optimal for this problem, as generating all subsets inherently requires O, 2 to the power of n, operations, and the additional O, n, factor for copying subsets is unavoidable when storing results. Finally, a quick mathematical proof confirms these complexities. The total number of subsets is 2 n, the total cost of copying subsets is n*2 n1, and the recursive calls amount to 2 n. For space, the recursive stack requires O, n, and result storage takes O, n*2 to the power of n. Thus, both time and space complexities stand at O, n*2 to the power of n. When working with subsets problems, there are several common mistakes you want to avoid. First, it's important to remember that subsets focus on combinations, not order. For example, if the input array is 1, 2, the subsets are 1, 2, 1, 2. Notice that 2, 1 is not included because the order does not matter for subsets. Make sure to clarify whether the problem is asking for subsets or permutations, as this distinction is critical. Another frequent oversight is forgetting the empty subset. The power set always includes the empty subset, so ensure it's accounted for in your implementation, whether you're using recursion or an iterative approach. Additionally, duplicate subsets can arise when the input array contains repeated elements, such as 1, 2, 2. This can lead to results like 2, 2, unless you handle duplicates carefully. A common strategy is to sort the array and skip duplicate elements during backtracking. Recursion errors are another pitfall. Forgetting to terminate your recursion properly or failing to explore all possible paths in the recursion tree can result in incomplete solutions. Lastly, iterative methods can sometimes become overcomplicated. Instead of modifying the existing list of subsets in place, focus on dynamically appending new subsets at each step to avoid unintended side effects. Now, when preparing for interviews, there are several key insights to keep in mind for subset problems. Recognizing patterns is crucial. Most subset problems revolve around two main approaches: iterative construction, where you start with an empty set and build up by adding new elements, or recursive backtracking, which systematically explores all subset paths. If the input includes duplicates, interviewers often want to see how you handle them. Sorting the array or using a hash set to eliminate redundancy are effective strategies to discuss. Optimization is another area to highlight. Generating all subsets inherently has a time complexity of 2 to the power of n, so focus on clarity and correctness rather than trying to reduce this unavoidable cost. Be ready to discuss edge cases as well. For instance, what happens if the input array is empty, like nums equals? Or if there's only a single element, such as nums equals 1? Make sure to confirm whether duplicates are allowed in the input. Finally, it's helpful to relate subsets problems to others that share similar concepts. For example, LeetCode 90, subsets 2, extends this problem to explicitly handle duplicates. LeetCode 46, permutations, shifts the focus to generating all possible orderings of the elements. LeetCode 784, letter case permutation, introduces subsets with letter case variations, and LeetCode 39, combination sum, asks you to generate subsets that meet a specific target sum. Additionally, there are alternative approaches you can consider when solving subsets problems, each with its own trade-offs. One method is bit masking, where subsets are represented using binary numbers. You generate all 2-in combinations by treating each bit as an indicator of whether to include a specific element. This technique is efficient for small inputs but can become challenging to implement correctly when dealing with larger arrays or arrays that contain duplicates. Another popular approach is recursive backtracking. This method explores every possible subset by deciding for each element whether to include or exclude it. It's intuitive and works well for handling duplicates, but it requires careful management of the recursion to ensure correctness and avoid missing paths. Finally, iterative construction begins with an empty list and builds up by adding elements to existing subsets. This method is straightforward and easy to follow, but adapting it to handle duplicates can be more challenging. Each of these approaches has its strengths and weaknesses, so it's useful to understand when to apply them based on the problem constraints and requirements. Great job! Here's a quick recap of the key points we covered today. We learned how to use backtracking to generate all subsets, discussed its time complexity, and explored its broader applicability. Thanks for joining me, and don't forget to subscribe for more problem-solving sessions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!